Okay, good evening, everyone. Please give a reaction if you can hear me loud and clear.
It's not clear.
Not clear.
You are far away from the device.
Mr. Freeman, is it not clear on your end as well?
It's not really that clear.
Oh, okay. Let me check it. Is it still unclear?
It's better now.
It's better now. Okay. So then, good evening, everyone. In today's lesson, we'll be continuing from where we left off in our previous sessions. Seeing as there's been a lot of time since our last meeting, I would like to know, would you like us to go over the first few lessons leading up to this one, or we should just proceed from where we left off for the sake of time?
For, for me, we should start, but if you want to continue, we can.
Start afresh.
Okay, all right. Is everyone in favor of that, or it's just the two?
Yeah, you.
All right. Let me allow everyone's mics so that I won't have to be going back and forth. Yeah. Okay, so if you have any contributions to add, you may unmute and then speak. But please, for now, let's keep our mics muted. Mr. Joshua,
Yeah,
please,
yes,
your mic.
your screen is showing an annotation to. Can you take it out? Because we can't see the screen.
I can't hear you clearly, actually.
Your screen is showing an annotation. Can't see the screen.
My screen is showing what? Ma'am, I can't catch what you're saying, quite.
An annotation to something on the screen.
Something is on my screen.
Yeah.
Yes, I am sharing a screen. It says conditional probability. Is that what you are implying?
We can't see that. I'm seeing an annotation to. Annotation to.
Oh, and Mr. Freeman, do you see my screen, please?
Yes, please. I see your screen.
So, Mr.
I think
Joshua, it's a network problem on your side.
no, he's seeing what I'm also seeing. Says
What is he
Prince
saying?
Wilson is starting annotations.
Oh, okay, I see.
But what I'm seeing is conditional probability. Understand
Yeah,
probability. That's what I'm
I,
seeing.
so, yeah, exactly. So, it could be a network problem. Okay, thank you for clarifying it. So, you
So
said we should go back to the first few lessons. So, let's go back there and then. So, Mr. Freeman and the rest, is it still the same?
I'm seeing the screen, but he was also seeing in addition to the thing, then that message as well. So that's what he was saying.
Okay. I understand. All right. Okay, so introduction to statistics and probability. We have been looking at this course since the start. Since we are starting afresh, then I'll give the very same advice I gave to those who started with me from day one, that this course on its own, honestly, it is not a course that is difficult. And then even the calculations and workings are not difficult. The main problem with the course is how big the formulas are and how sometimes they are hard to interpret. So an advice to you, for whenever you're learning any subject that has to do with mathematics, just bear in mind that nothing is too hard. And don't just see it as something you're telling yourself. It is actually what it is. Maths never disappoints once you understand how it goes. It's not like English where you can make some, verbal flaws and whatnot. Or it's not like science where you have to memorize and then reproduce exactly as was given to you. Maths never fails as far as you get the fundamentals. So now pertaining to this course, the formulas are the most confusing parts. And if you're able to understand the formula and interpret them differently, then I believe you have the course as good as understood. So let's start. Whenever there is a formula, I'll try to simplify it in a way that we will understand better. And I'm challenging myself to see how confused I can leave you at the end of the lesson. Okay, let's go. Okay, so in today's lesson, we'll be discussing concepts like a random experiment, and we'll be looking at a random variable. Then we'll look at different ways to define probability, and we'll look at the axioms and laws that define probability, and also look at mathematical expectation if time permits. Let's breeze through this very fast. So then the basics. So the purpose of this session, let's focus on this. At the end of the session, you should be able to differentiate between random and then events and random variables. You should be able to give examples of random events and then random variables. You should be able to define the expectation of a random variable, and you should be able to compute the expectation of a random variable using a given probability function. So an experiment, we are looking at all the terms here. An experiment is a process of observation. I believe you know this. Random experiment is any experiment of observation or activity in which the results cannot be predicted with certainty. So these are events that are not biased in nature. What this means is that given a random experiment, even though you know what the outcomes might be, you cannot specifically tell that it's going to be this or that. For example, in a coin toss, you can tell with certainty that there's going to be either a head or a tail, but you cannot specify which of the hair faces is going to land. Therefore, we consider such experiments a random experiment. Another example is a die toss, or when you pick a card from a standard deck of 52 cards. All right. Alternatively, an experiment or random experiment is any specified set of actions where the results cannot be predicted with certainty. So that's exactly what we just said. Now, whenever we do an experiment more than once, we say we have done trials. What this means is that if I take a coin and I toss it once, I toss it twice, each toss is an experiment. But then as I multiply my tossing, then I have doing what I call trials. So on the first toss, I had one trial. Second toss gives me 2 trials. Third toss gives me 3 trials. So then the experiment is what you are doing, and then the number of times you do it leads to a trial. Typical examples of random experiments include the rolling of a die. So when you roll a die, it's a random experiment since you cannot tell the outcome. Tossing a coin might give you a head or a tail. You cannot tell what exactly it will be, but you know that it will be either a head or a tail. Okay, selecting a ball at random from a box containing 3 balls marked ABC. Also a random experiment since you do not know what you are exactly drawing. Let's proceed. Now, in describing an experiment, the following terms are employed. We employ terms like outcomes, events, sample space. Let's look at what these terms mean. An outcome is the result of an experiment. So when I toss a coin and it lands on heads, that is my outcome. If I toss a coin and it lands on tail, that is my outcome. The outcome basically describes what exactly comes out of the experiment. So then the end goal of that experiment is the outcome. The outcome is different from the expected outcome. The expected outcome is what you expect to come out of the experiment. So you expect a head or a tail. However, the outcome is what exactly happened. So when I toss the coin, my expected outcomes were heads and tails. However, my outcome might have been a head since the coin might have landed on a head. So that is the idea here. Now, when we take an event, we say an event is any collection of outcomes. So when you take several outcomes, you put them together, you get what we call an event. So for example, we toss a coin 3 times, and then we get we get 2 heads or 3 heads. This becomes an event. So the event of a head or 2 heads or 3 heads occurring. It's a number of outcomes put together, whether it's 1 outcome or 2 outcomes or 3 outcomes put together. That is what an event is. Now, a simple event is an event with only one possible outcome. So as I mentioned earlier, whether it's 1 outcome, 2 outcomes, 3 outcomes, but when it's specifically 1 outcome, you classify it as a simple event. So for example, what are the odds of tossing a 6 when a fair die is tossed once? Then the probability of you getting a 6 is just 1 out of 6 chances. What this means is that you have described a simple event. So a simple event is one that has only one possible outcome and only one. Example, in tossing a fair die once, the possible outcomes are 1, 2, 3, 4, 5. The collection of one or more of these possible outcomes is an event. So the probability of you taking a 1, 2, or 3, or taking a 4, putting these two together is what gives you what we call the desired outcomes or the outcomes. Moving further, the sample space. For a given experiment, the set that contains all the possible outcomes is the sample space. So then we mentioned earlier what possible outcomes are and how they differ from outcomes. Outcome tells you the exact value that comes out of the experiment, whereas the expected outcome tells you what desired or what possible result you are going to attain at the end of the experiment. The sample space takes all these results and puts them in one set. So the sample space is basically a collection of all your possible outcomes. And that is all there is to it. So now questions may flow like, what is the sample space in a single toss of a coin? Then your sample space is head or tail. What is the sample space when you roll a die, a fair die, a fair 6-face die? Then the sample space is you getting a 1, 2, 3, 4, 5, or a 6. So basically the set of all possible outcomes is what we call the sample space. In a sample space, we have all the values in there may be defined as single outcomes. Each single one is known as a sample point. So the sample point is defined as one possible outcome of a random experiment. So in the example of tossing a fair coin, whether it's a head or tail, the head or tail becomes what we call the sample point. Now note the difference between the sample point and the outcome. The outcome is what exactly comes out. The outcome is exactly what comes out, whereas the sample point here talks about one of the possible outcomes. Doesn't necessarily say it actually occurs, but one of the possible outcomes. So whether it's a head, whether it's a tail, that is the sample point. Note that a set with one sample point is often referred to as an elementary event. So then when you do a set and then you are supposed to identify one sample point, or when you are given a probability and then the sample point just has one possible sample point, like one possible outcome, then you go further to say that it is an elementary event. It means it's on its own, exactly. Now, assume A is a set A. It's called a subset of B. This is denoted by A subset B. If every element of A is also an element of B. Now, any subset of the sample space is called an event. If you remember set theory from when we were doing maths for 105, DCIT 105 in level 1, semester 1, you realize that these set notations, and also even in senior high, these particular set notations over here, they are used to express different meanings in sets. And this one, for example, is what talks about subsets. So when a set is written like this, or when a notation is given as this, you say that A is a subset of B. And then this means that every element of A is also present in B. So now they are saying that for any given sample space, any subset of the sample space is called an event. And then we know that when we take a Ludo die, for example, all the events happening on it, or all the possible outcomes are 1, 2, 3, 4, 5, 6 on a single toss. Now, combining one or two of these gives you what we call a subset of the sample space. Subset is basically a set that contains elements like what you see here that belong to this universal set over here. So then A is 2 of 3. Set B is 1, 2, 3, 4. So all these, we can say that A is a subset of B as you see here, considering the fact that all the elements of A are also given in B. And you may also say that B is a subset of the universal set, which is the sample space. So you see A is a subset of the sample space, whereas B is also the subset of the sample space. So they are implying that for any given event, it should be a subset of the sample space, else it's an impossible event. So for example, if I tell you I'm tossing a die, what is the chance of me getting an 8? When the die is a 6-face fair die, the event of me getting an 8, or the chance of me getting an 8, is impossible, considering the fact that 8 is not one of the elements in the sample space. So if you are a subset of the sample space, then it means you're a possible event to occur. If not, then you are outside. You are impossible. The sample space S is the subset of itself. That is, S is a subset of S. Since S is the set of all possible outcomes of the experiment, it is often referred to as a certain event. So for example, if I ask you that when I toss a coin, what are the chances of me getting either a head or a tail? Your answer is supposed to be exactly certain. You should be able to tell me that once I toss a coin, if I don't get a head, I will still get a tail. So when they say either a head or a tail, what this means is that the probability of me getting a head is fine, or the probability of me getting a tail is fine. And since both head and tail are the entire sample space, because when you toss a coin, the sample space is just head and tail, the probability of you achieving the sample space is a certainty. Like where then out toss a coin now, when your head, ubenya tail. So then when we say either a head or a tail, then it means we are defining the entire sample space. And since the sample space is a subset of itself, and every element present inside that subset is the same as what is in the sample space, then we conclude that the sample space, the probability of it occurring is exactly 1. In other words, it's a certain event. So what if I ask you, when I toss a die, what's the probability of me getting a 1 or a 2 or a 3 or a 4 or a 5 or a 6? Just go back to logic, right? In logical mathematics, when we're doing logics, DCIT 102, DCIT 104, whatnot. You know that in Boolean logic, when you do additions with all phrases, the truth table says that either when one is true and the other is false, it is still true. And when both are true, it is still true. So what this means is that if I ask you for the probability of me tossing a 1 or a 2, look at the keyword I'm using, or a 2 or a 3 or a 4 or a 5 or a 6. I'm asking that what's the probability that I can get anything on the face of the die. I'm not asking for an individual element, but I'm saying that what's the probability that I can get anything on the face of the die? What this means is that I have given the chances of me going into the sample space and then actually picking something. So it means what's the probability that when I toss the die, I will get a face, basically. So what's the probability that when I toss a die, I'll get a face? And that is a certainty, because there is no way you will toss a die and not get a face. And this is what it means when we say the sample space is always a subset of itself, and then it is often referred to as a certain event. All right. Here's the first example. It says we are to find the sample space for an experiment of tossing a coin repeatedly and counting the number of tosses required until the first head appears. So now what this means is that we are doing the coin toss. It is different from your average probability question. This one says we are not just tossing the coin. However, we are tossing it and see how many times we must toss before we get a head. So now look at it this way. When you toss the coin, you might toss it the first time, and after tossing it, you might get a tail. It means on the first try, you didn't get your tail, right? It could be that on that first try, you actually got your tail, but you didn't get a head. And this question says that we have to find and count the number of times we need to toss until the first head appears. So what this means that on your first toss, you might get a head. So your sample space can contain 1, which means 1 toss. Secondly, it might be that you toss first time, you didn't get it, so you had to toss 2 times before you came across the first head. What that means is that your sample space can also be 2 tosses. It can also take you 3 tosses to get to the value you want. It can literally take you 1,000,000 tosses before you can get the value you want. Therefore, we write the sample space as S is equal to 1, 2, 3 to positive infinity. Like we basically do not know where it ends. It's not continuous. We just don't know where it ends. So it's, as we said, it's unpredictable in nature. Since we cannot tell what the defined sample space is, we can only give an estimate and say that it will keep going until, because it might take me 2 tosses to get a head. It might actually take someone 500 tosses to get the first head. So it differs from person to person. Therefore, we do not know where exactly, unless we were told how many tosses were done. So if we were told how many tosses were done, then it means it's either from 1 to 0. Because what this means is that you can, let's say you are doing 10 tosses. You could do 10 tosses and not get a head after 10 tosses. So it means this time it was impossible, right? So then this one here defines how many tosses you do to get a head, basically. That's what you're seeing. The next one says that let's consider the experiment of drawing 2 cards at random from a bag containing 4 cards, which have been marked with the integers 1, 2, 3, 4. So assume you have a bag, and then inside the bag, there are 4 different cards. Each card has the markings 1, 2, 3, 4. Now, we are supposed to find the sample space. In other words, we are supposed to put all the possible outcomes in a set. So the sample space defined as S1 of the experiments if the first card drawn is not replaced. So let's say you take out the first card, then you do not put it back, yet you take the second card, then you take another, then you take another. After picking 2 cards, the question is, what exactly is going to be the sample space? So in other words, you're looking for the possible combination of events that we can get. So it can be a 1 and a 2. It can also be a 1 and a 3. It can be a 1 and a 4. It can also be a 2 and a 3, a 2 and a 4. So there are so many combinations. With this particular question, using a tabular form to represent it is the easiest way to see how the sample points can come about. So now let's look at what this could be. So let's consider what our possible values are. Currently, we have 1, 2, 3, 4, as you can see over here. Now we are to inside our bag. So let's list here for sample space 1. So I'll draw this table here. Okay, something like this. So event 1. So what if we pick a 1, right? We could pick a 2, we could pick a 3, and we could pick a 4. So now let this side of the table outline what the first picks could be, okay? And let this side of the table be what the second picks could be. So we could pick a 1, we could pick a 2, we could pick a 3, and then we could pick a 4, like so. So now let's try to see. Remember that according to the experiment, when we pick the first card, we do not replace it. So it means there is no way we can pick a 1, 1. Mr. Emmanuel, please unmute and speak.
Please, I don't know if it's from my end, but the screen, some read only, you can only view annotations, like it's occupying some parts of the screen, and I can't see everything you're doing.
Really? Is that true?
Yes, sir.
Okay, I'm coming. And then there is no option to make it exit or something because it's not displayed on my screen actually.
Yeah, I'm seeing some cancel, but I think you can do it from your end. There's a cancel sign here.
No, you are seeing that, but honestly, I am not seeing that. The screen I see doesn't have that actually. So it is on your side, so you can hit the cancel. Is it cancel or like an X button that lets it disappear? And please, how many of us are facing this issue?
Okay, so one has gone, but the second one, I think that one too is from your end. But I think
Which second one?
it's better not.
Is that which second one actually? I'm sorry.
Like
I do
one
not
is at
see
the
that.
top. It's not that visible.
It's a bar. Is it a bar? Just a bar that you see the pens and what's not on top. Is that it?
Yeah. Some read only something, but it's better
I
like
do not see the read only thing. Okay, so find an X button and then try canceling it since you can. Sorry. Okay, let's proceed with this. Or perhaps I should stop sharing screen. The same thing there.
The same appeared on my screen, but I was able to cancel it.
Okay, so Mr. Venix, please, what do we call it? Take advice from those who are speaking now. They say the same thing happened, but they were able to cancel it. All right, let's proceed. So then if we are doing the pairing, on the first toss, we could get a 1. But remember, not the first toss, on the first pick, we could pick a 1. But remember that we are not replacing the card. So if we pick a 1, we cannot pick a 1 again, considering we are not replacing the card. So there is no way we can get a 1 and a 1. So this box is out. On the second pick, so on this first pick, we could pick a 1. That's true. And we could pick a 2. As for that one, is very possible. It could also be that on the first pick, we actually picked a 1. And then on the second pick, we rather picked a 3. It could also be that the first pick was a 1, but the second pick was rather a 4. So this is possible. We could also, instead of these combinations, get on the first try a 2 and get a 1. But we cannot get a 2 and a 2 since we didn't replace the 2 card. However, we can get a 2 and a 3. And you may also get a 2 and a 4, like so. It could also be that your first pick was not a 1 or a 2, but rather it was a 3. And then your second pick was a 1. Could also be that the combination is rather 3 and 2. It could also be that your combination is rather 3. No, so now your combination cannot be 3 and 3 because after picking 3, you didn't replace it, right? So it cannot be 3 and 3. So it could be that your combination is rather a 3 and a 4, like so. And it could also be that your first pick was rather a 4, followed by a 1. Second pick was also a 4, but this time followed by a 2. Third pick was a 4, followed by a 3. Sorry, your pick was either a 4 and a 1, or a 4 and a 2, or a 4 and a 3. That's what I meant to say. But there is no way your pick, yes. Okay, there is no way your pick can be a 4 and a 4 since you didn't replace it. So what this means is that the sample space, yes, Mr. Samuel Ajite.
Yes. Yo, please, are you
Yes.
writing on the screen or
I am.
are you writing? Well, we know the
I
C.
am, yes.
Or
Ah,
like we know the C. I know the C.
I can see
Please, is it-
clearly.
who said they can see clearly, please?
Can you?
Oh, so Mr. Sammy, you be that you be like you be network problem
Yeah,
from
we
the
knew.
side, so check out. Boss, you be like you be
So make
network
a
problem was
rejoin
happening.
now.
Yeah, region. You went region.
Okay, yeah.
All right, fast. Okay, so seeing this, then we can list our sample space 1 as all the possible combinations that came out of this set. So what this means is that in our sets like this, we are going to have the first event 1, 2. It's a possibility. We could also get, instead of 1, 2, we could get 1, 3, as you can see from the combinations here. So like this and all. Don't worry, it will be done on the next page. So now let's count how many combinations we got from here so that we can be sure. So over here we get a 1, 2, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the sample space is going to be what you get when you put all these individual combinations inside the set, as you can see me doing over here, like this. So this is basically what the sample space is. In other words, all the possible outcomes of the toss. Are we clear? So now that is it for sample space 1. So in sample space 1, since we don't replace the card after picking it, there is no way you can get the same card twice. Now, if you go to sample space 2, that's question B over here. Look at what it says. It says we have to find the sample space S2 of the experiment if the first card drawn is replaced before the second one is drawn. So over here, there's a difference between the first and the second. In the first one, we're not replacing, so you cannot get the same card twice. But over here, since you pick a card and replace it before you pick the second, right? What this means is that there is a chance of you picking one card 2 times. So if we are to do the sample spacing for the second question B, then what you're going to get is you could possibly get a 1 and a 1. Because now you are picking and then replacing. So you just might pick a card, you replace the game. Over here, you could pick a 2 and a 2, like so. You could also pick a 3 and a 3 because you're replacing the card. Remember that. And you could also pick a 4 and a 4. What this means is that this one gives us more elements in the sample space. So over here, if we count, there are 4 columns, 4 rows here, 4 columns. That gives us 16. So then the sample space S2 is going to be what we get when we put all these 16 combinations in one set. So then you start by fixing in your 1, 1, doing same for the next element all the way to the last, element. And you over here, so you do same all the way to the last element. So I hope this is clear. It's a basic concept actually. Is this clear, or is there any question that you want to ask before we proceed to the next slide? Okay, looks like there is none. So let's proceed. Okay. So now, as you can see, question 1 says that the sample space for S1 contains 12 ordered pairs, where I and then J, where I is the first draw and J is the second or the final, and blah, 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 all the way to the end, and blah, blah, blah. So it says 1 is less or equal to J, and J is less or equal to 4. So J is a number between 1 and 4. I is also a number between 1 and 4, from 1 to 4, exactly. The first number indicates the first card drawn. So we have the combinations as 1, 2, blah, blah, blah. Same situation in the second one, what we just explained previously. So since no hands went up, I assume there are no questions, so we proceed. Let's move on. So another example says that we have to find a sample space for the experiment of measuring in hours the lifetime of a transistor. Now for this particular one, it's an event that can take possibly forever. Because think of it, a transistor is a device that operates on its own, not like it operates on its own, but you get the idea. The lifespan means that how long will it take till the device gets damaged, right? Or how long can it function as it's supposed to? As far as I'm concerned, unless you're able to know certain data, it is almost impossible to predict when the device is going to stop working. Unless, of course, the device is made of a particular element that you know will go bad in a given amount of time. That aside, it is hard to tell whether this device is going to stop working now or is going to stop working in a million years. Like, time is endless and time is a continuous value. So for that reason, this type of probability is said to be a continuous probability. So now let's see the differences between discrete and continuous data. So now note, it is useful to distinguish between two types of sample spaces, discrete and continuous. A sample space is discrete if it contains a finite or countable infinite set of possible outcomes. In this case, the elements in the sample space can be listed or the list does not terminate, as in example 1. So then if you go back to example 1, as you can see over here, we can count from 1 to 2 to 3. But then I told you that you do not know specifically how many tosses it will take you to come by the first head. Therefore, despite the fact that this is discrete, it is still an endless data. It's infinite. That doesn't mean it is continuous. Now, let's see the difference between discrete and continuous data. Now, when we take discrete data is data that can mostly be counted. So like data that does not require precise measurements to accrue is what we call discrete data. So for example, you go into a room and you count how many shoes are there. Such data is discrete because there is a fixed number of shoes that there can be in that given room. Here's another way you can look at it. Let's say you are told that there were 5 eggs in a bowl and then someone has eaten 2. Or no, not even say someone has eaten 2. Let's say there were 5 eggs in a bowl and you are told that some of it has been eaten. Good. And I ask you to go in there and count how many eggs are in the bowl. There is a limited number of values that you can bring to me back after counting the eggs. You can either get 1 egg, 0 egg, 0 eggs, sorry, 1 egg, 0 eggs, 2 eggs, 3 eggs, 4 eggs. But since we know that someone has eaten some, there can't be 5 eggs, right? So then there is a predictable, in other words, there is a very limited range of events, and we can easily see where it starts and where it ends. And the in-betweens too are clearly defined. So it's either a 0, it's either a 1, a 2, or a 3, or it cannot be a value in between 0 and 4, like 0 and 1, like 0.1x or 0.2x. Like it is well defined and then it's distinct from all the other values given in the set. So it's not in a range. And even if it's in a range, it can be easily ascertained from the range. That's the whole idea. So then a sample space is said to be discrete if it contains a finite or countable infinite set of possible outcomes. So like in the case of when we're tossing a coin to see how many heads it takes, as far as we can count how many tosses we do, even if it takes 1 billion tosses, as far as we can count how many tosses it took us to get that, then we consider it to be discrete. So countable, fixed value within a range is what we call discrete data. Now, a sample space is continuous if it contains an interval, either finite or infinite, of real numbers, as seen in example 3 above. Now, mind you, the fact that we are talking about real numbers doesn't necessarily mean that it will always have to do with decimals, or that discrete data doesn't have to do with decimals. The main idea is, can it be counted or can it not? Now, in a sample space for continuous data, we do not look at what we look at is what the value can take in a given range. So for example, if I give you a range as how tall can a person be between 4 feet and 5 feet, right? And I give you about 300 people and I tell you to measure their length. And I'm supposed to give their length, like give the length of their height or whatever with a particular range, like give their height. This is going to be very difficult, seeing as when you measure height, there might be subtle differences between the heights. Someone might be 5 feet tall, someone might be 5.1 feet, someone might be 5.15, someone might be, depending on to what place you are rounding to, there can be just between 5 and 6 feet, several values, like it's literally endless if you want to count the decimal values, because numbers are infinite and decimals also go on forever. The range between 5 and 6 for the decimal numbers or real numbers is basically endless. So then if we say the sample space is continuous, this is what we are talking about. We mostly look at values that are measured. And then these values are characterized by being able to assume any given particular value in a given range. So the height of a person between 5 and 6 feet, it can literally be anything. However, when I gave you the example of the eggs, when you went into the room, there are a fixed number of outcomes there could be. You cannot have 5.2 eggs left. Even if you come and tell me that there is only half of an egg left, you are still implying that it's half of one egg. So then since you can count it, then it is discrete. When it's continuous, it's uncountable. When it is mostly measured, like temperature, time, temperature to particular ones, right? Sometimes in some situations, you can consider it to be discrete. But then when it's used not as a measurement, but it's used as a count for comparison sometimes and other things, keep that in mind. So now it says like an example 3 above, example 3 shows continuous data. So then you see, we do not know when exactly the transistor is going to die out because we are dealing with time, and time is also a continuous event that is basically endless. So for example, if I take your age, you might think your age is actually a discrete data, but then since ages are measurements of time, then technically they are also continuous data. Think of it this way. If we want to calculate the age of a baby, right, it can take on any value depending on how much into detail we want to go with the dates or with the age. For example, if you decide to calculate the age in seconds, then it becomes a fraction of a day. If you want to calculate it in days, it becomes a fraction of a month. If you want to calculate it in months, it becomes a fraction of the year. This means this can give you different decimal values. For example, if I tell you that a child is 1 year old, but I have to calculate precisely how old they are, taking into account the hour they were born, the time of the day, the minutes, blah, 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 you realize that there will be discrepancies between the 1 year olds. And even when a child is like 2.4 hours, someone can be 2.41 hours old, 2.43 hours old. So technically, age is also a continuous variable. A random variable, usually written as x, is a variable whose possible values are numerical outcomes of a random phenomenon. So when we conduct a random experiment, what we defined earlier to be an experiment whose outcomes are not known with certainty, then we are saying that if you are conducting an experiment on a particular variable, like when you are tossing a coin, the outcome of a head or a tail is a random variable, seeing as it is coming from a random experiment. So random variables are basically possible outcomes of a random experiment or a random phenomenon. Alternatively, a random variable is a variable whose value is unknown, or a function that assigns values to each of an experiment's outcomes. So now you may define the random variables as, or designate letters to them such as x, y, or z, and these can be classified as discrete. And we mentioned earlier, there are variables that have specific values or continuous, which are variables that can have any value within a continuous range. Am I going too fast, or is the pace good and perfect?
Even if you go slow, self will be challenged.
Who that? Round one, are you sure this level is already a challenge? Hey, then we die, yo.
This
Oh,
one
tell me
they
how
touch
this is.
you.
Hey. Hey. Oh, are you sure? So you mean say so far, what are they give? No, you know the bar. We
You
just study
watch
calculate
Ballon d'Or
here.
ceremony.
Hey, Bema, are they go? Okay, so A typical example of a random variable is the outcome of a coin toss.
Them they give
So when you're
Ballon
tossing
d'Or.
a coin, Bema, it's you. Now, when I toss a coin, since I do not know specifically what I could get, then technically this is a random variable. So now this one says, let's say we are tossing a coin, and then we say the random variable y is the number of heads we can get from tossing 2 coins. Then y could be any of these values. When I toss the coin 2 times, it could be that both of the tosses will give me a tail. It means I get 0 heads, as you see here. It could be also that one of the tosses was a head and the other was a tail, so it means that means it gives me 1 head. Or it could also be that both tosses were heads, so I get 2 out of 2. So then the random variable y may assume any of these values. It could be 0 heads in 2 tosses, 1 head in 2 tosses, or 2 heads in 2 tosses. This means that we could have no heads, 1 head, or both heads on a 2-coin toss. That's the idea. Examples of discrete random variables include the number of children in a family, the Friday night attendance at a cinema, the number of patients in a doctor's surgery, the number of defective light bulbs in a box of 10. So basically, values that you can count are random variables that are discrete, so discrete random variables, whereas ones that are uncountable and can only be measured to quantify are said to be continuous random variables. Examples are your height, your weight, the amount of sugar in an orange, the time required to run a mile, etc., etc. It can assume any value within a given range. Okay, the chance and the assessment of risk play a part in everyone's life. So we are moving into probability and we are going to define it. For example, if you're a loan officer, you should be able to ascertain that in a country such as Ghana, or if you go to a country like America, you should be able to ascertain the rate at which people default after they take their loans. Ghana had the say very high. What the loan name at Ghana was so that there's a high probability that the person taking the loan takes that loan and then the person knows you know more. And sometimes you even meet them face to face and they're like, I don't know you, or what do you mean I took a loan from you? This whole thing means to a loan officer, in order to avoid losses or in order to bring your loss to a reasonable amount, you have to understand probabilities well so that you can ascertain the risk, how high it could be and how low it could be. As an investment officer too, you should be able to tell just what the risk of losses are and how high they are as compared to profits. So you are going to invest into a business, you realize the business's all its success rates. Who said it business no a failure. Don't be a messiah and say, perhaps I'm the one to cause the change. Unless you want to do, then since the probability of the business succeeding is not 0, then it means there's a chance. Just that chance is far lower than the probability of it failing, seeing as it has failed countless times. Or when you're going to do a bet and then the odds are stacked, Pampe on one side, they've given 5 CD to one team, the other team gets only 1 CD. You should be able to see that the risk of winning at the back of the team that has 5 CD is low. That is why they've increased the odds over there. And the risk of winning where the odds are lower is high. And that's why they have decreased the value over there. And then this ascertaining your risk, knowing where to go, where not to go, these are uses of probability. So it has found a wide range of business applications such as calculation of risk in banking and insurance industries, quality control, and market research. Most events in life are unpredictable. I believe it's unpredictable. So events in life are non-deterministic. Please, no offense to the West. So events in life are non-deterministic in nature. What this means is that you cannot tell what exactly the outcome will be. Even if you know what they can be, you do not know what they will be. Now, if the world is treated as stochastic, then we can measure the chances of any particular outcome happening in a given situation. So if we assume like every event, or if we assume that we can control certain events to a certain level, if we assume that we can control how many students come to school in a day, then we assume also that we can calculate the probability of a boy child coming to school. Now, remember that we are saying stochastic. This means that there can be real life fluctuations, but assuming, that's what you should have. So assuming the world is treated as stochastic, then any particular situation can have a particular outcome, and its probability can be properly counted or measured. Probability is the measure of the likelihood of the occurrences of an event. So how likely an event is to happen is the probability. How likely is it to rain tonight? What's the probability of it raining tonight? The probability of an event can be thought as thought of as the relative frequency of the events. We know that in relative frequencies, we define it as taking one frequency and dividing it by the total frequency, right? So then the probability of any event happening is also giving us one element inside the sample space divided by the sample space. What this means is that technically we are doing frequency over total frequency. So probability is relative frequency of a given event. So the probability of an outcome can also be interpreted as a subjective probability or degree of belief that the outcome will occur. So then the degree of belief will range between impossible and certain. So for example, you can talk about some events being highly likely, others being less likely. Like if I ask you, what's the probability of the world ending tomorrow? Now, don't look at it from a Christian perspective and tell me that we do not know, right? Now, if I tell you to give me on a scale of 0 to 1, how likely is the world to end tomorrow? This is not 50-50. Because if we take into account all the factors that can end the world, then it means we can somewhat, that's why we are saying treating the world as being stochastic, having control over certain values, then we can somewhat ascertain that the world is not likely to end tomorrow. I'm saying don't look at it from a Christian perspective. Look at it from world-ending events that could take place, like a nuclear event that could destroy the world, or what's the called? We call it a meteor big enough to destroy the world, suddenly crashing into it, or the earth suddenly rupturing and then spreading into bits, or the sun suddenly engulfing the earth and the earth disappearing. How likely are these events to happen, taking into account what it was like right now? Then you might be able to say, oh, it's likely, it's unlikely, it's very unlikely, it is impossible, it is certain. So it means you can describe these values with a degree of belief or how much you believe the thing can happen. That's what it means in this point. Probabilities are numbers between 0 and 1. So you cannot have a probability less than 0, a probability greater than 1. And you should take note of this question. Sometimes you will be asked to talk about, or you may be given objective questions, and the questions could be that given which of these values is not a probability. Just look out for the negative numbers and the values greater than 1. Any other value that is a fraction or is 1 or is 0 is a probability. So 0 is a probability, and then that's an impossible probability. So when the probability is 0, it means it cannot occur. And when the probability is 1, it means it will definitely occur. Other definitions of probability are relative frequency, classical definitions. Now let's look at them. The probability, let's look at the relative frequency definition. The probability of an outcome is interpreted as the limiting value of the proportion of times the outcome occurs in n repetitions of the random experiment as n increases beyond or about. What this basically means is, for example, you go into a classroom, what's the probability of you picking a boy in a class where there are 3 girls and then 2 boys? It's just basically the number of boys in the class over the total number of people in the class. So then it just defines one event over the total possible number of events. So then the outcome is interpreted as the limiting value of the proportion of times the events can occur in how many times the experiment has been conducted on the sample space, basically. So for example, if we assign a probability of 0.4 to the outcome that there is a defective item in a production batch, now we might interpret this assignment as implying that if we analyze many items in the production batch, probably or approximately 40% of them will be defective. Seeing as we've been able to calculate the probability and now we know it's roughly 0.4, which is 4 over 10, the same as 40 over 100. This means out of every 4 or out of every 10 devices, 4 of them are most likely defective. Out of every 100, 40 of them are mostly defective. Therefore, we may also rewrite this probability as a percentage and say approximately, you see the way they are saying roughly 40% of them are defective. This example illustrates a relative frequency interpretation of probability. So it talks about parts over whole, parts over whole. So part of the probability over the sample space, relative frequency definition. So we're just looking at how to define it. So then it's given here as the limited value or limiting value of the event in question. For example, this one over the sample space. So in other words, how many ways or how many times the sample space, how many times the favorable event occurs in the sample space over the sample space. Stated differently, the relative frequency can be stated as the ratio n of A over n for the probability of A if n is a large number. So the number of times A can occur over the sample space, basically the same thing. Now, when the likelihood assumption is not valid, relative frequency method can be used. The relative frequency technique leads one to conduct an experiment n times and records the outcomes. Now, the probability of an event A is assigned by, so you say the probability of A, read this carefully, we'll be using this later in our lessons, like we are doing probability sorter. So probability of the event A is equal to number of favorable outcomes of A. So how many ways A can occur over N, which is the sample space, where F of A denotes the number of experimental outcomes that satisfy event A. In other words, favorable outcomes for A. So now let's look at an example here. It says that the table below shows the frequency of grades in statistics class. And then it says that these are marks, and we are talking about how many times the marks were gotten. Papa Penitra 60, 3 got 75, 478, 580, 783, all the way to 99. You can see what's happening there. Now, the relative frequency for the mark 90, that means the probability of you getting the mark 90 is going to be frequency of 90 over total frequency. Now, in the question, if you add all the frequencies here, the total frequency is 63. The probability of you getting a 90 is the number of people who got 90 over how many people took the test. This is the relative frequency definition. So frequency of those who got 90 over total frequency, in other words, how many people took the test? 5 over 63. Expressed as a decimal as 0.079, or you may write that as a percentage, 0.79% or so. Right. Also, the relative frequency for obtaining a mark less than or equal to 83. So if we consider 83, this one says a mark less than or equal to. Now I want you to take very good note of these terms, the words and or in probability. You see, they both point out to different ways of working. Whenever you hear or, it wants you to do a union, or it basically wants you to do an addition of probabilities. So probability of A or B occurring is just probability of A occurring plus probability of B occurring. So remember, whenever you hear or, you just need to add or combine events. And whenever you hear and, you don't need to do combination or you don't need to do addition of events. So we'll look at n later, mostly goes to multiplications. Right, so now this one says that what is the probability of getting a mark less or equal to 83? So it means the mark can be 83 or it can be any other value that is less than 83, as you can see here. This means that it could be a 60. So we need to know the probability of getting a 60 or a 75 or a 78 or an 80 or an 83. So then they are just basically asking probability of we getting any of these values, any of them. Since it says this or that, all you need to do is find the probability of getting a 60, add that to probability of getting a 75, add that to 78 all the way to 83. And that's what you can see happening here. So it's 1 out of 63 for the probability of getting a 60. It's 3 out of 63 for probability of getting a 75. And then all the way to 7 out of 63 for the probability of getting a 7 and an 83. And then you know that when you're adding fractions and the denominators are the same, you always look for a common denominator. And since they are all the same, you just put them together as one value, as you can see here, and then blah, blah, blah. So then that gives you 20 over 63 expressed as a decimal as 0.31. Using the relative frequency definition, now we can therefore estimate probabilities. Thus, the probability of obtaining a mark 90 is 0.79, as you can see here. That's how many people got 90 over the total number of people. And obtaining a mark less or equal to 83 is 0.31. That's how many people got less or equal to 83. That's combining every value for the probability under 83 and equal to 83 and dividing it by the sample space 63, and then it gives you 0.31. All right. In an experiment for which the sample space is S and the outcomes are equally likely, that is, each outcome has the same chance of occurring, then the probability of an event A occurring is given by the formula probability of A is equal to number of outcomes in A over total number of outcomes. Now, before I go ahead to explain this, what is an event or what is an experiment you can do that has all the events on its face or all the events that can come out of it being the same? Like in that experiment, if I want to calculate what the probability of a particular event is, that probability is going to be the same across all events inside the experiment. Can you give me an example of such an experiment?
The probability of
Yes,
tossing,
you can do.
Yes, please give one.
a coin, either getting a head or a tail.
Exactly. So you see that he says probability of tossing a coin, you either get a head or a tail. So it means probability of getting a head on a coin toss is 1/2. That's the same thing for probability of getting a tail on a coin toss. That's also 1/2. Therefore, we assume that in this, then the outcomes are equally likely. Fun fact I heard recently, and I don't know if it's true, that actually when you toss a coin, the probability of you getting a head or a tail is not 50-50, and there is more to it than meets the eye. That's an interesting concept for another time. Let's continue. So now the probability of A describes the number of ways that A can occur, like what we already talked about. Basically, it's the same thing. So all the definitions are basically pointing to the same thing, just that they are all applied differently. But each and every single one says number of favorable ways the events can occur over the sample space. So over here says number of ways it can occur over the sample space. And you see it's no different from what you saw here. That also says favorable outcomes of A over the number of events that could take place, and over here, or the frequency, relative frequency of all the way, the same thing. So the probability of A is the fraction of the total number of outcomes that cause the event A. Okay. Now, let's suppose that in a box, there are 5 balls in a box, and then 3 balls are red, 2 are black. Now the box is shaking, and then the ball is selected without looking. What is the probability that this ball is red? This is just going to be the number of red balls over the total number of balls, right? So then the probability of picking a red ball is going to be number of red balls, which is 3, over total number of balls, which is 5. And that's what you can see here. And this is the basic probability formula that says that favorable outcomes over sample space. That is all. Or number of possible outcomes. That is all. Okay, let's look at this one here. Now, in a group of 400 college students.
Please, can you clean the writings on the screen?
It was still there all along.
Yeah.
Wow. And nobody said anything. You see, I've hidden it on my screen, so I have no idea. Sorry. Okay, it's gone now, right?
Yeah.
I had hidden it on my screen, so I didn't know it was there. Oh, and it will be uncached. All right, let's continue. So in a group of 400 college students, it says that there are 170 science majors, 230 non-science majors, and of the science majors, 55 are women, and there are 120 women who are non-science majors. One student is selected at random from the group, and find the probability that the selected student is a science major. Now you see the table they have done here, and mostly when you're dealing with probabilities that have a lot of values, right? You are advised to use a diagram, like use a probability tree, which we'll be looking at later in conditional probabilities, or use a table. Now the table, just as you saw in the first question that we treated, the table helps us to easily group all the possible outcomes. And then the same thing has been used here. Else you will have a lot of data to be looking at and you might end up confused. So now see the solution. It says that it has tabulated nicely. The science majors, according to the question, 55 are women, 115 are men. And then it says that the non-science majors, 120 are women, and then 110 are men. Combining the number of women will be 55 of the women in science major plus 120 non-science major. That gives you 175 women. Do same for the number of science majors, 55 plus 115, you get 170. Non-science majors is 120 over plus this, that gives you 230. And then same situation for the total number, that's men plus women on both sides. That's 400. So now we have to first find the probability that the selected student is a science major. So we are trying to calculate the probability that we are taking someone at random and the person is a science major. Can you tell me what this one will be? Remember, number of favorable outcomes over total number of possible outcomes. So which values are we going to use to calculate probability of there being a science major? So raise your hand, raise your hand, and then share if your name is mentioned. Mr. Felix Freeman, yes?
I would take the total for science major to be 170 divided by the total of 400.
Okay, 170 over the total of 400. So Mr. Freeman says that for his probability of picking a science major, then he's going to take total number of science majors, that's 170 over total number of people, which is 400. Do we agree with his suggestion?
Yes.
Yeah, I agree.
Yes, sir.
Okay. Yes, sir. So this means that the total number of science majors is 170 over the total. Because the favorable outcome we are looking at in this case is 170 for the science majors over the number of favorable outcomes. See the way we overlooked every other value there and went straight ahead for what is expected. So it says favorable outcome. So do not be confused by how much data you have. Just look for the favorable outcome. Just look for the total for basic probability questions. That is, when the questions progress further, you realize that sometimes you need more than this data. But then for now, just look at the basics. Now, what's the probability of selecting a woman? Probability of selecting a woman, what will it be? Yes, Mr. Freeman. Yes.
175 over 400.
Exactly. So 175 over 400, because there are 175 women here. When you add the women in the science and the non-science, that's 175. And over the total, that's 400. Now, the probability of the person neither being a woman nor a science major. So it means they are not women, they are not science majors. If you are not a woman, it means you're a man. And if you are not a science major, it means you are what? A non-science major. Mr. Freeman, yes?
110 over 400.
Okay. So he's right. Okay. Then the question says that you are neither a science major nor a woman. So it means you have to be a man, one, and you also have to be a non-science major. And then the number of people who fall into this category is 110 people over the total number, which is 140. Remember that always leave probabilities in simplified forms. Or if you cannot simplify, just convert them to decimals and then leave them as is or write them as percentages. You are advised to do so. One of the major reasons is the fact that it makes marking easier for the examiner. And also, when you're doing objective type questions, there's a fine chance that you will not see your answer in its complex form inside the list of answers, unless it is simplified to its simplest form. But the simplest form is basically the average value that every student can enter. Fractions are equivalent in nature, so it means if I have 2 over 5 as my answer, someone can also have 4 over 10. Someone can also have, let's say, what is another equivalent for 2 over 5? Let's say 5 over 20, right? All these ones go to say that if the person has given this value, everybody's answer is different. How exactly does the lecturer take his time to analyze all these and convert them into the simplest form to see? So you are advised whenever you're working probabilities to leave your answers in the simplest form or in decimal forms. So then let's look at the next page here. And now it says that for the number of people who are science majors, the probability of getting a science major is 170 over 400. A woman is 175 over 400. Probability of getting neither a woman nor a science major is 110 over 400, just as Mr. Freeman defined. Mr. Freeman, big ups to you. No congratulations. But clap for your hands, my brother. Clap for your hands. Okay, we'll proceed. So now, here's another one that says the axioms of probability. Now, the axioms of probability are like basic defining features of probabilities. So these features are what every probability will in the end be qualified by. So they define what the probabilities are, most especially 1 and 2. Axiom 3 is only got to do with union of probabilities, but then it still defines across probabilities, by the way. Let's start with axiom 1. Axiom 1 says that a probability is always between 0 and 1. That's the first axiom. So what this means, not even, so it says 0 and 1 inclusive. It means 0 is, it could be a 0, 1, 2, sorry, it could be a 0, it could be a 1, or it can be any value in between. But then it's written as the probability, 0 is less or equal to the value of any given probability, and then the value is also less or equal to 1. So it can be 0, it can be any value between 0 and 1. It can be a proper fraction, not an improper one, because that will give you a value greater than 1, right? So probabilities are always either proper fractions, 0 or 1s. Okay, that's the first axiom. This means that if I give you a question and I ask you which of these is not a probability, and I give you values like -3, 2, 4, 6, your answer is supposed to be all of the above, because all of them are not probabilities. I mentioned 2. 2 is greater than 1. I gave you -3. It is also less than 0. I gave you 4, 5, 6. All these values are greater than 1. And then they are not in between 0 and 1. Neither are they equal to 1 or less than 1 and then greater than 0. Therefore, you assume or you say that they are not probabilities. So remember, axiom 1 says probabilities are always between or from 0 to 1. Axiom 2 says that the probability of the sample space is always 1. It's always certain. So we looked at that earlier as a axiom. What this means is that when you conduct an experiment, the probability of you getting an outcome at all is always a certainty. There is no way you will toss a die and then before the die touches the ground, it just vanishes into nothingness. Unless, of course, you have some black magic. That being said, we don't think we do. Therefore, whenever you do an experiment, there is always an outcome. Like there always is an outcome. And that outcome is what we define the sample space as. So the sample space is all the possible outcomes. So the probability of attaining any value in the sample space is always a certainty. Therefore, it's always 1. And the probability of attaining a value outside the sample space is always 0. Like I mentioned earlier, on a coin or a die toss, there is no way I can get 8 when I toss a fair die. Now, unless you are into gambling, then the only dice you are familiar with is the one with the 6 faces. That doesn't mean there are not other dice. We have some dice that have 7 billion faces. We have some dice that have 12 faces, 13 faces, 16 faces. But then on a standard die, a 6-face fair die, whenever you toss, there is no way you can get an 8, right? So what this means is that the probability of 8 occurring there is a 0. So basically, probability of an event occurring outside the sample space in an experiment is what we are saying is impossible, so it's 0. Axiom 3 says that if A and B are mutually exclusive events, then the probability of A union B is equal to what you get when you add probability of A to probability of B. What does this mean? Suppose you go into a place and then I ask for a number of boys, number of girls. The number of boys will be for a specific group of people and the number of girls for the specific group of people. There is no intersection between the boys and girls, right? For this reason, if I want to know the total probability, it will be the combination of the probability of boys plus the probability of girls put together. What this means is that there is no intersection, so we can just go ahead and add both probabilities. The reason why you need to consider the fact that intersections exist is that sometimes the intersection, not all the time, intersection will happen at more than one place. So for example, we are looking for boys, we are looking for girls, and there is someone there. Oh yeah, I don't know how I'm supposed to. I don't say Kojo is here because they are not necessarily boy or girl. Maybe more again or way. But so we then they have a vagina as well. So where do they fall? Should we add them to the boys? Should we add them to the girls? Right? This person becomes an intersection. It's just a nine that found. Therefore, they become an element that belongs to both sets. So if I want to count how many people in that room, I cannot count that person twice. Like let's say I've counted the number of boys and I counted him as part of it. I counted the number of girls, I counted him as part of it. If there are supposed to be 20 people in the room, then there will be 21 because one only we're counting the 2 times. So what this means is that for probabilities that have intersections, you cannot just combine them and say you have the total probability, but rather you're going to have to subtract the intersection from it. So nipa baako na ɔyɛ hermaphrodite na ogyina fa no, you have to subtract him once. So after adding him on the first side and adding him on the second side, take him out once so that he now occurs only once. That is for events that are dependent. So dependent events are events that have intersections. But then when we say the event is mutually exclusive, mutually exclusive, or you say it's independent, yeah, we are implying that both events do not have an intersection. Therefore, there is no common ground between them. And if you want to find their total probability, you can just combine the probability of both events. Big sorry to all those who have been in the class from the start, okay? But those who have joined us late, they said they want us to go back. But don't worry, we have calculated how much time we have. And we also calculated the probability, you see, of we being able to complete what we are supposed to before the time we have is up. So, we last. Okay, next one. So now in the sample space S, now if the sample space S is not finite, so it's infinite, then A must be modified as follows. So a given probability A, the union of all the possible events happening will be the probability of A occurring plus that of B occurring. Probability of A, let's say the events are given as A1, A2, blah, blah, blah. Then it's supposed to be the probability of A1 plus A2 plus A3 to positive infinity. Now I want you to take note of what they did over here. You see how they said the probability of A intersection B occurring is equal to 0. What this means is that there is no intersection between them. Therefore, as we explained earlier, they are mutually exclusive. Therefore, if you want to find their total probability, just add. Let's proceed. Now, this means that, for instance, if A1, A2, A3 are events that cannot occur simultaneously, you can't say simultaneous as anything.
They can't occur at the same time. When you say something simultaneously, it means that the occurrence of one has a relation or depends on the occurrence of the other.
Oh, okay. Please, who is speaking?
Freeman.
Mr. Freeman, as for you, dear. Okay, yeah. So as he said, simultaneous events are events that are affecting each other when they occur. So you see, when you are doing simultaneous equations, you must take into account one equation in order to solve the other. So they are literally events that happen. They can happen at the same time and also affect each other when they do occur. So now it says when you have two events and then they are not simultaneous in nature, it means the occurrence of one doesn't necessarily influence the occurrence of the other. Then you assume or you say that they are mutually exclusive. There is no common ground in between. So for example, the probability of either rolling a 2. Huh? Okay. The probability of either rolling a 2 or a 6 when you toss a die. This time, since we know that there is only 1 2 on the face of the die and there is only 1 6 on the face of the die, and then 2 and then 6 do not share any correlation whatsoever, like there is literally no intersection between them in this instance, right? Then we can assume that the probability of getting either, and you see either goes with or, you see 2 or a 6. I mentioned earlier that whenever you see or, this keyword prompts you to do addition. Then we just have to add the probability of getting a 2, which is 1 out of 6 faces, right? Plus the probability of getting a 6, which is also 1 out of 6 faces. And then summing that up gives you 2/6. That's the third axiom. So the third axiom says for mutually exclusive events, just sum them up if you want the joint probability, that's all. Okay, so now, quick recap. What does the first axiom of probability state? Can I remember out of it? Hey, can you hear me?
Please, the question again.
Okay. I was saying that, let's say, sorry, let's not say anything. What are the axioms of probability? What does the first axiom of probability say?
I can
Just a
remember
quick recap. Yeah.
the one is saying that a probability is between 0 and 1.
Exactly. That's the first axiom. So probabilities are always between 0 and 1. Congratulations, boss. You've just got that down. Okay. And what's the next one? Yes, Mr. Imanoni Papakoti. Let's go.
Yes, the probability in the sample space is always equal to 1.
Okay. Okay. So is your screen fine now, Mr. Imanoni?
Yes, sir.
All right. Mr. Freeman, yeah, let's hear from you, boss.
The probability of an event occurring in a sample space is 1, and then of an event that is out of the sample space given is 0. The probability of that event is 0.
Okay, exactly. That completes axiom 2. And then axiom 3 is what you're looking at, that for mutually exclusive event, the union of events is just the sum of both probabilities. Next one, let's keep going. I like the way we are moving. Okay, now let's look at the properties of probability. Now, the axioms of probability define probabilities. They talk about how probabilities come about, rules that probabilities should follow, provided they belong to particular groups. Axiom 1 and 2, they are constant for all probabilities, whereas axiom 3 is only for mutually exclusive events. Now we look at the properties of probabilities. These properties are what help you do probability operations faster. In other words, they make probability operations simpler when you're working them. Let's look at the first probability. First probability says that for a given event A, the probability of A occurring can be written as P of A. The probability of A not occurring is going to be total number or total probability, let me call it the total probability, okay, minus A. In other words, what? Okay, as I was saying, for a given event to occur, A, it may be defined as PA, probability of A. The probability of A occurring will be probability of A, but the probability of A not occurring is going to be the sample space minus A. I hope that is understood. I go into a class. There are 5 students. 3 of the students are boys, 2 are girls. Probability of picking a boy is going to be 3/5. Probability of not picking a boy is going to be the total sample space, which is 1, right? Total probability, 1, minus probability of picking a boy, which is going to be 1 minus 3/5. So in other words, whenever you are to find the probability of an event not occurring, just find the probability of the event occurring and subtract that probability from 1. And then you get its complement. So the probability of an event A, the probability of A complement is going to be 1 minus probability of A. And that is what you are seeing here. So property 1 says that to find the complement of a probability, just subtract the probability of 1. Are we clear? And it is important. You will need it for weekends. It makes you fast. Okay. Next one says that, so for example, if the probability of obtaining a 6 when we roll a die is 1/6, then the probability of we not getting the 6 is sample space 1, right? Minus probability of getting a 6, 1/6. And that gives you 5 out of 6 chances. The property 2 says that the probability of an event that is not in the sample space, in other words, an event that is null, not in the sample space happening, is always 0. And we've talked about this countless times, that if the event is outside the sample space, it just can't happen, so it's impossible, basically. Here property says that. So now let's take a good look at this. In the previous slide, we just talked about mutually exclusive events, right? So now let's talk about the union rule. The union rule says that provided you are combining 2 probabilities, if they have an intersection, that's if they do have an intersection, the joint probability is going to be what you get when you add both of them and you subtract the intersection. Like in the case of what I described the first time, grouping a class into men and women and having a hermaphrodite in there. Then first counting him amongst the men when you inspected the men's private parts, and then counting him amongst the women when you inspected the women's private parts. Oh my God. Yeah. Since you have counted him 2 times, this means that if there were supposed to be 20 people in the class, that person has been counted twice, so he makes the number 21. So in order to find the actual number of people in the class, what do? You subtract him once. So you have to subtract how many times the intersections occur from the total probability. So that's what you can see here. Provided 2 events are not exclusive. So you see it says event A is a perfect subset of B. What this means is that all the elements of A can be found in B. Therefore, we say that the 2 events are exactly the same. And since they are not the same, they share some similarity. So if you want to combine them, you have to subtract the similarity so that you do not combine it 2 times. Just like in the case of the counting I keep using, because I believe it will stick. You cannot forget the fact that you are inspecting private parts for men and then doing for women. Just remember the fact that you cannot count one individual 2 times just because he belongs to both groups. As far as you're looking for the total number of people in the class, he only counts as 1 person. So then the combined probability for dependent events, in other words, events that are not mutually exclusive, events that occur simultaneously, good. These ones are done by combining the events and subtracting the intersection. So now, finally, if A and B are mutually exclusive, then the probability of A intersection B is 0. So the formula can just become probability of A union B is the probability of A plus B, like we just talked about that. So if the events are mutually exclusive, they share no intersection, right? Now over here, it says that given this, combining 3 different probabilities, Then in the three probabilities, let's say there is an intersection for A and B, an intersection for A and C, and also an intersection for B as well as C. Then the joint probability is going to be just what we have done up here, combining A. Sorry, I'm coming in. Good. The joint probability is what we get when we combine probability of A with that of B with that of C, as you can see here. And then we go ahead to subtract the probability of A intersection B since they share a similarity. So you see what we did in the earlier lesson, just that this time on a larger scale. And then you subtract the probability of A and C occurring as well. And also subtract the probability of B and C occurring as well. And finally, you add all that to their joint intersections. This might not be clearer to see, but do you remember three set problems? Let's draw one, and then we will see what this really means. So now, draw this bigger. Okay, so now we have three different sets here. Now let's say there are intersections. This side has a value, this set here has a value of, let's say, 5 or something. This side has a value of, let's say, 4. This side has a value of like 3. And then the two of them share an intersection. So let's say I tell you that this side is 1. The intersection between 3 and 4 is 1. Let me tell you this side is 2. And then the intersection for this side is, let's say, 3, like this. And I tell you that all three of them have a joint intersection. In other words, there is a value that happens at all the places. And I tell you that maybe that value is something like 8 occurs once, right? Then if I want to find the total or the union, the universal set here, I'm going to have to add this one to this, and add that to the intersection. Why I'm saying that is, you see, if I want to find the value up here, like this, I'm going to have to do 4 minus the intersection, right? So I'm going to have to do, so if I want to do the value here only, I'm going to have to do 4 minus all the intersections, and that will leave me with the value here. If I want to find the value here as well, I have to do 5 minus all the intersections, which will not make sense technically in this one. But then it's just a question you can see. If I want to find the value here, so I have to do 3 minus all the intersections. These are what will give me the values here, here, and here. Now, if I want to find the total number of people, I'll have to add this only, that's this side, to this side, add that to this side, and finally add all of that to the joint intersection. All these intersections over here, they disappear. And that's what you are seeing here. So then when I want to put all these values together, I will have to subtract all the individual intersections and maintain the joint intersections of all the three elements like this. Okay. Right. Let's proceed. So suppose events A, B, and C have the probabilities A is equal to 1 over 2, B is equal to 1 over 3, C is equal to 1 over 4. Furthermore, assume that A intersection B is 0, so there is no intersection between A and B. B intersection C is 0, and A intersection B is 1 over 6. Let's use the agents of probability and then properties to find out all these values. Let's start with the value here. The probability of A, what's my time? It's running out of time. The probability of A and B not occurring. You see the thing? It says the probability of A intersection B complement. What this means is that the probability of A and B not occurring. Can anyone tell us as to what exactly or which rule we are supposed to apply here? Remember, if you want to do intersection, so please let's listen to this. The intersection that you are looking for has already been given here, 1 over 6, right? But in questions when it's not given, mostly, not always, mostly, Mr. Freeman will come in here. So for questions like this, mostly but not always, you will just have to multiply both events to get the intersection. So the probability of A times probability of B will give me probability of A intersection B. So as you can see here, probability of A is 1 over 2, probability of B is 1 over 3. Multiply this and you get exactly 1 over 6. That's probability of A intersection B, as you can see here. So now using the equations of probability, let's see the probability of A and B not occurring. Okay, Mr. Freeman, please, you may speak now.
Okay, so the probability of A intersection B occurring has been given. So for short, I would use property 1 if I'm right, and I'll take the probability of its occurring from the total probability. That is 1.
Oh, okay. Oh, okay. Thank you. That's exactly it. So as Mr. Freeman has well stated, he says that we have been given the probability of A intersection B to be 1 over 6, as you can see here. So since we know that it's 1 over 6, and we mentioned in the property 1 that if we know an event occurs and we know the probability for that, then the probability of its not occurring is just subtracting its occurrence from the sample space. So then the probability of A intersection B complements probability of intersection B complement is just going to be total probability, as he said, 1 minus 1 over 6, as you can see here. This simplifies to 5 over 6, but then what the hell, let's just solve it. So the LCM is 6. You use the calculator anyway. The denominator here is 1. 1 goes here 6 times. 6 times the numerator 1 is still 6 minus 6 goes here once, and then 1 times 1 is 1. So 6 minus 1 gives you what? 5. And then your denominator is still 6, as you can see here. Therefore, the probability of not getting A intersection B is 1 minus probability of getting A intersection B, which is 1 over 6, and that gives us the value 5 over 6. Let's move on to the next question. Probability of getting A intersection B complement. See the difference between the first question and the second? The first one was A intersection B all complements. Now this one is A intersection B complement. So the probability of getting an A and also getting the fact that the probability of B not occurring. So probability of getting an A and B not occurring. Remember, in order to find these values for intersections, as you can see here, just take probability of A and multiply it by probability of not B, as you can see here. Okay, so now let's find the parameters that we need first. So the probability of A, we already know it to be 1 over 2. That's here. So we have the probability of A is equal to 1 over 2. And then the probability of B has also been given as probability of B, what is it? 1 over 3, right? It's 1 over 3. So now to all my very attentive listeners, what do we do to find the probability of B not occurring? So please, Mr. Freeman, this one I want you to allow. I want to see what the others two have to say concerning this. So how do we find the probability of B not happening? If we know that the probability of B happening, okay, yes. Mr. Joshua, let's go.
Okay, can you say 1 minus 1 over 3?
Thank you. So exactly what you can say, yes. So then you take the total probability, which is 1, and you subtract the probability of B happening to get the probability of B not occurring, 1 out of 3. So you can look at it as a classroom. You went in there and then you found 3 boys. What's the probability of not finding a boy? You just take the number of people in the class minus the number of boys, right? And then that gives you the remaining class, which has no boys amongst them. So then we do 1 minus 1 over 3, and that brings us to exactly 2 over 3. Or you can go ahead and do the calculation and see, but let's just do it, okay? As I keep saying, what the hell? So 1 over 3. Our number 1 here is a whole number, so it's over 1. The LCM for these two values is 3. 1 goes here 3 times 3 multiplies the numerator and gives us 3, right? Subtract that. 3 goes here 1. 1 times 1 is 1, and 3 minus 1 is over, right? And then we get the 2 over 3, as you can see over here. So then the probability of B complement is this. That's 2 over 3 here. So now the question says that it wants, they're not done. The question doesn't want all this we have done. What the question really wants is the probability of finding A intersection B complements. Or did I just clean that? Okay. The probability of finding A intersection B complements. So in other words, we need the probability of A as well as the probability of B complements. And then since it says end, the probability end mostly goes with multiplication. So since it says end, let's multiply both probabilities, shall we? So then someone should help us and walk us through the multiplication. How will it be? So B complement is 1 over 2 over 3. A is 1 over 2. Okay, then let's just go ahead and do it. So then the probability of A intersection B. Okay, Mr. Kayum, yes. Mr. Kayum may speak.
Yeah,
Mr. Kayum, yes, please.
we are doing multiplication. Probability
Yes,
of A, which is 1 over 2 times.
Yes, sir.
Probability of B complement, which is 2.
Okay. 2 over 3, thank you. So then as he said, since it's probability n, which is an intersection, if it was all, then we'll be adding, that's the union. But then since it's n, he says we multiply, so 1 over 2 for A, and then 2 over 3 for B complement. And that gives us 1 times 2, that is 2. The multiplications are direct, no LCM needed. 2 times 3, that's 6. This simplifies to 1 over 3, or it stays 2 over 6. But remember, it's best you leave it as its simplest fraction form. Thank you, Mr. Kayum. We will stop the session shortly, but I want us to just complete these, what do we call it, so that we don't carry it into the next lesson. Next one says probability of A union B, all complements. A union B, all complements. Now, can anyone help us before we do this? Probability of A is A and B, are they mutually exclusive or they are dependent? So to those who have not spoken, am I allowed to mention your names? No, let me relax. Anyway, can anyone walk us through how, or before then, are they mutually exclusive or they are independent? Or they are dependent, sorry. Studying the question, will you say A and B are disjoint or they have an intersection? Yes, Mr. Kayum.
They have an intersection.
They have an intersection. Okay. Mr. Kayum, because we're taking, sorry. Okay, so this means that since they have an intersection, then if we want to find a union, then we have to add both events and then subtract the intersection. I hope you remember that, so that you do not do double counting. So now, someone should raise their hand and walk us through how exactly, step by step, we have to calculate this. Let's assess ourselves and see if we are learning or not. Okay, Mr. Felix, let's go.
So because this event is not mutually exclusive, that means they depend on each other. Okay. I would say that this is the probability of A occurring plus the probability of B occurring minus the probability of A intersection B, that is both of them occurring at the same time.
Okay, so you say probability of A
occurring
plus
the probability of B occurring.
The probability of A plus that of B minus their intersection.
Yes, please.
All right. I believe that is correct. Okay, so Mr. Bright, your hand was up. I want to believe that you can walk us through what comes next, right? So help us insert the parameters. Okay, yes. So yes, let's go, Mr. Bright.
Yes, so it's going to be 1 over 2 plus.
That's A. Okay.
Yes, for the
1
A.
over 2.
Yes, for the probability A. Yes, and then and the B plus 1 over 3.
So plus 1 over 3. B. That's right. Yeah.
Yes.
All minus.
Yes, all minus 1 over 6.
1 over 6, which is the intersection B. Well done. Thank you, boss. So 1 out of 6. So then we deal with the additions in the bracket first, right? So this is going to be, let's see what we have here. 2 multiplies 3, that gives us 6, right? And then we have 3 times 1, that's 3, plus 2 times 1, that's 2. So that's 5 over 6. So we are left with 5 over 6 for what the bracket used to be, or for what the bracket represents. And then we are subtracting the intersection, which is 1 out of 6. Okay, so what will this amount to? So 5 minus 1, since the denominators are the same, they combine into 1, that's the LCM. And then 5 minus 1 gives us 4 over 6. This simplifies to 2 out of 3, by the way. So 2 over 3. Okay, we are making progress. I like this. Okay, let's look at the next question. This one says we have to find a complement.
It's not completed though. It left with the complement.
Hey, thank you. Hey, you see what we just did, what I just did, sorry. I have just computed the probability of finding A union B. Thank you. Who is this? Who pointed this out?
It's Kayu.
Charlie, I will momo you to office, so make you the space for your accounting side. All right. So now, as I was saying, you have seen that we have clearly calculated for the probability of A intersection B, the probability of A union B, but the question didn't ask for that. It asked for their complements. Therefore, we have to find the complements, and we can do that by subtracting A intersection A union B, sorry, from 1. So thank you, Boss Kayu. So then the correct answer to this is going to be yes from 1. So 1 minus 2 out of 3. 2 out of 3 being the what we call it, A union B, mind you. So then what would this give us? This is going to give us what? 1 over 3, or let's see. Then the intersection here is, sorry, the LCM here is 3. 1 goes into 3 times 3, 1, 3. Minus 3 goes here 1. 1 times 2 is 2, and that gives us what? 3 minus 1, that's 2 over 3. Is that right? All right, let's test that. I think that is not correct, right? So 1 goes here 3 times 3, 1, 3. 3 goes here, good. So 2, 1, 2. That's true. So 3 minus 2 gives us 1. So the correct answer is 1 over 3. You see that? 1 over 3. So these are the small things that we should look at, like what Mr. Kayu pointed out here. A small detail I missed. It will not merit me the full mark. And this time we are working objectives in statistics. What this means is that you just might see your correct answer to be 2 over 3 when there is 1 over 3 there. If you stopped your calculation at this point, this is what you might go for when you were supposed to go for this. So let's bear that in mind. Okay, let's move on to the next question. Probability of A complement intersection B complement. Yes, let's raise hands and then try. So remember this probability end. So you just find A complement, multiplies by B complement, and you're good to go. To find A complement, refer to property 1. Mr. Bright, let's go. I like that.
Not answer at the moment. Please try again later. Sorry, the person's call did not answer at the moment.
You find the complement of A,
okay,
and then the complement of B. So the complement of A is going to be 1 over 2 minus 1.
No, you mean 1 minus 1 over 2. Right?
Yes, 1 minus 1 over 2, sorry.
Exactly.
1 minus 1.
Yes, and then, so 1 minus 1 over 2, and that gives us 1 over 2, since 1 minus half is half, right?
Yes.
So 1 over 2, excellent. And then the next one, we need a B complement. So what would that be?
B, yes. That's
what would that be?
The B is 1 minus 1 over 3.
1 minus, okay. 1 minus 1 out of 3. And this one gives us exactly 2 out of 3 like this. So then their intersection is just going to be A complement times B complement, right? Yes, sir. Like this. Like this. So then we have 1 over 2, that's A complement, multiplying 2 over 3, that is B complements. 1 times 2 gives us 2, and then 2 times 3 gives us 6, and this simplifies to 1 over 3, like this. So then A complement intersection B complement is 1 over 3. Now let's look at the final one, and then we end the lesson with that. So remember, for when there are more than one, you are supposed to combine. You first have to find probability of A plus that of B plus that of C. Then you subtract probability of A intersection B if there is some. Then subtract probability of B intersection C if there is some. And you subtract the probability of A intersection C2 if there is some. And after doing this, you add all that to the probability of A intersection B intersection C. So you add the joint intersection after you have subtracted the individual intersections. So now let's see what this comes down to. So who would like to walk us through this tedious process? Okay, so then we do probability of A. So please follow. We add that to the probability of B. So from what I explained with the set diagram, you have to find all the individual intersections and subtract them. And when you are done, add the joint intersection. So we are combining A union B union C. So probability of C, we combine that as well. And then we consider the intersections. So let's start. They said A intersection C, there is nothing there. So there is no intersection A intersection C to subtract. So that removes one intersection. There is no B intersection C to subtract as well. So that removes another intersection like this. And then the probability of A intersection B occurring, that one was given. So the only individual intersection we can subtract is probability of A intersection B. All the other ones are 0, 0, by the way. So subtracting zeros will make no difference. Okay. So the probability of A intersection B, blah, 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 blah. And then finally, and finally, we have this. Now, provided there is a joint event for all three, so provided there is A intersection B intersection C, then we are going to have to add that to it when we are done. But if there is none, then this is what your combination is going to be. Then you do the addition. Okay, so you add A, you add that to B, you add that to C, you subtract A intersection B, A intersection C, and B intersection C if they are there. But as you can see, they are not. The only individual intersection we're given was A and B. We are subtracting that. And when you are finally done, you also add the joint intersection of all three if there is one. And that gives you the final answer. So we've come to the end of today's session. Let's look at the answers to what we were supposed to get and see if we were able to nail them correctly. All right, so let's start. For the first question, as you can see, they obviously applied property 1 and subtracted, and they got 5/6. For the second one, they took a different approach, and then they used a particular property of probabilities, and then they ended up with the same answer we got, 1/3. So you can basically do what we did. Just find, please, there is a mic unmuted and it's distracting, very distracting. Please mute.
Yeah, Mr. Jackson, tomato.
Yo, okay. Yo, Fumato, your mic is on.
Please, can you clean the screen?
I've cleaned it all. Wait here, paper. Yes, I you don't get to have clean. Hey, it's there. Nah, it's really there. It's really there. How about now? Is it gone?
Yeah, it's gone.
Is it? Okay, sorry. Okay. So now, as I was saying, you see they use a different approach, but they arrived at the same answer. So you can just basically go with what we just learned, find probability of A, multiply that by B complements, and then you arrive at the same answer they got 1/3. A simple concept. Probability of A union B complements is just 1 minus probability of A union B. And then as you can see, since A and B are dependent event, they subtracted the intersection. In the end, they had the same answer. We had 1/3. Now over here, they used De Morgan's law. De Morgan's law distributes intersections over unions and then unions over intersections as additions. So as you can see here, it distributes multiplications over additions, and then it distributes additions over multiplications. This has been used a lot in Boolean logic, and it makes you understand these things very easy. This is one way we can solve the question we just solved, and you see we arrive at the same answer, 1 out of 3 or 2 over 6 that we just got here. So you see we found A complement multiplied by B complement and blah blah. Right. And finally, the last question, as you can see over here, since A intersection C is 0, B intersection C is 0, then it follows that A union B intersection C is also 0. So what this means is that there is no joint intersection for all 3 events due to the fact that there are 2 events in there who do not have intersections. So there is no way all 3 events occur at the same time when some of the events are not sharing relationships. Good. So then what you can see here, the probability of intersection B intersection C, this one combines A union B plus that of C as well. And then it's what you are seeing over here. So we've come to the end of today's session. Let's see what comes next. So currently we have just 7 slides to go and we complete lesson 1A. So next time we meet, maybe I don't want us to, but maybe we'll do a brief recap on what we did so that we can move on, because we have a lot of ground to cover in statistics. If this was a revision lesson, by the way, normally I still go fast, yes, but for this one, since it's a lesson we've treated 2 times actually, and we are doing it again, that's in just my sessions, not the lecture sessions, that will mean that we have tackled this far too many times. That's why I'm rushing through fast. And I'd like to believe, at least I deceive myself, that the goals for the lesson have been met. Do we agree?
Yes, sir.
All right. I'm glad it was helpful. So I'll step aside for Mr. Evans to come in. Oh, Mr. Freeman. Sorry. Mr. Freeman.
It was a mistake. Sorry.
It was a mistake. Oh, okay. I'll step aside for Mr. Evans to come and give us a little something. So, Mr. Evans, please, are you there?
Yes, sir. Yes, sir.
All right. So let me stop sharing and then you take over.
All right. Okay. I hope we are all and